So just a recap, a lot of this we just heard from Brendan, so I won't spend a lot of time on it, but you know, there's two forms of virtualization that we have on the system. We have the OS virtualization, which we just talked about, and then we have the KVM, QEMU style of virtualization, which essentially runs a VM with a separate operating system. Hopefully, between what Brendan just said and all the, you know, since zones have been out there for a long time, hopefully people are pretty familiar with that. There's a lot of information you can find out about how zones work and things, so I'm not going to actually dwell a lot on the details of that. The key differentiator here is that we've got the single OS kernel when we're doing OS virtualization, so you don't have that layered effect and you don't have that, you know, have the same effects that Brendan was talking about. If you want to learn more about QEMU in the work that we did there, Brian did a good presentation last year at the KVM forum, and you can actually go watch his presentation there to see more about how the KVM works. So most everything that I'm going to be talking about here is related to OS virtualization. One of the things, I'm not sure if it was so clear in the previous presentation, but we actually run, even when you're running a KVM QEMU in a non-native OS, we still actually run that inside of a zone. So we're always running each of our guests, each tenant is always inside of a zone. And the benefit there is, you know, we always can use the resource controls and the containment that the zone provides, even if you're also running inside QEMU. So what I want to do is I want to kind of review the enhancements that have been made in the area of OS virtualization, and really that breaks down into two areas. And hopefully, as I'm going through and talking about different things, you know, it doesn't come across too negative that we had to do so much work. But you know, I do want to reiterate that we actually are starting with a great foundation. You know, when Illumos started a couple of years ago and we started building SmartOS, you know, we already had, you know, Crossbone, dtrace, and ZFS, and all the great things that we get from Illumos. So, you know, what I'm going to focus on today is actually the things that we had to improve to make this really work well in the cloud. So, as I said, this breaks down into two areas: general issues, which I'll talk about first, and this is kind of a collection of just all sorts of things that we had to fix. So, if you're familiar with the old Solaris 10 zones, you might be aware that there was a thing called sparse zones, and that's something that no longer exists in Solaris. It didn't exist in Illumos when Illumos started, because the concept of sparse zones was very tightly woven with the old SVR4 packet system. So one of the first things that we had to do was we actually created a new kind of a brand that allows us to have some of the same attributes as the old style sparse zones. And the key thing there is that we get to share a lot of the core file system with the global zone. So each zone is using the lib and SBIN and user file systems from the global zone. So those are only exist once on the system. All the zones use them. And aside from the storage savings that gives us, we also get performance win there, because all of the zones, any zone running an application coming out of those file systems, it's going to be paged in, it's going to be sharing those same pages, it'll only exist in memory one time, you won't have to page it in because most likely, you know, PS is already going to be paged in if you run it, things like that. So that gives us a lot of benefits right out of the gate. The next area, I mean, we fixed a lot of bugs in the system to make zones work better. I'm not listing all the bugs here. I just picked out a few that I think are kind of interesting to quickly review. One of them, you know, these are in different areas. One of them is like PS. You know, you don't see this on a system that's maybe only running 10 zones, but if you've got a box running 100 zones and you run PS in the global zone, it behaves really badly. And, you know, we track that down to the way it was looking at like TTYs for processes in the non-global zones. We have to fix that. Another one completely in a different area is that if you have a zone that's trying to do a mount, that mount hangs for some reason, you know, maybe the server is gone, you know, or something like that, that actually will prevent all the other zones on the system from rebooting or, you know, booting in the first place. or shutting down. So that's actually kind of a critical problem that has been in the system ever since zones started, that we had to track down and fix not so long ago. Another bug that's very common is with the operators. A lot of times they'll log onto a box to start looking at what's going on and maybe seeing what's happening. If they happen to CD underneath the zone path, that process current working directory being in that zone path will actually prevent that zone from shutting down. So that's one that actually seems to happen a lot because the operators like to kind of log in and start moving around in the file system and things. So we actually did a bunch of work there to make it so zones could be resilient to that, and that we'd actually be able to detect when that situation was happening. Because what will happen is the zone tries to shut down or reboot. It's the same thing, and it gets blocked. Then the operator logs off, and the zone is still stuck. It never can finish. So we actually had to fix things so that it could retry and kill the process that's causing the problem. And then another one, kind of in a different area is in ZFS. If you delegate a data set into a zone, and then someone inside the zone actually creates a ZVOL, that will prevent the zone from actually booting up again the next time it tries to boot. So that's a problem in the system that we actually had to fix as well. So there's a lot of other ones. These are just some simple examples. So there's bugs that we fixed, and then there's general kind of improvements that we went through just to make quality of life better on the system. So this is simple things like making WAL work so that you can actually send messages across all the zones if you're the operator and you want to tell people something's going on, like a shutdown or whatever. We actually capture core files outside of the zone so that if there's a problem in the operating system, like service start, V core dumps or whatever, we want to be able to capture that and debug it as a general system kind of a thing. We don't care so much about the customer applications, but if one of the core system utilities core dumps, we want to know about it so we can figure out what happened and fix that. So we enhanced core Atom so that we can do that. A big area that we actually had to improve early on was vNICs. Because of the way that we actually manage virtual NICs on the system, those are managed and owned by the global zone, even though they're sort of handed off to each zone. And so one of the things that we want to do is have a nice friendly name, like net zero is what we call it, for each NIC in each zone. You can't actually do that on a stock Solaris system because the names have to be unique since they're owned by the same zone. So we actually enhance the system so that we can track vNICs by a combination of the zone ID and the zone name. We have per zone load averages, LX proc, if you remember the old LX brand that Solaris used to have, that doesn't exist anymore, but we resurrected the LX proc file system so that inside zones you can have some Linux tools like HTOP work, things like that. And then SMF, we actually put SMF on a diet. It wastes a lot of memory. The resident set size is, well, it's about 9 meg, and that doesn't seem like very much, but if you have 100 zones on the system, each zone is running its own instance of start and things. So, that quickly adds up to real memory that we were able to reclaim that can be used for doing real work. The other area that we've done a lot of work on in general is with observability. I think Ben mentioned this morning. Services have been enhanced to be aware of zones. In particular, one that I use all the time really is services minus ZX. And so that allows me to look across all the zones on the system and see if any zone is having a service problem. Instead of having to log into each zone, I can just, from the global zone, see right away if there's any zone with a service problem. I'm not going to go over the dtrace stuff because that was covered really well by Brendan already, but suffice to say we did a lot of work. Actually, the one thing I do want to mention that Brendan didn't cover is that analytics for zones were actually not very feasible because every time a zone boots, it gets a new zone ID. So if you reboot your zone, it'll have a different zone ID. So it's really hard to sort of trace and watch a zone over a long period of time. So what we did is we actually went in and added a persistent zone ID that allows us to be able to monitor zones over a long period of time and know that it's the same zone if you're doing analytics over a long period of time. The other ones I think Brendan already talked about there. And then finally in observability, we've added a lot of new case stats, as Ben mentioned this morning. He's a big fan of that, and I think most everybody enjoying it is. So we've added a lot of things there. I've summarized some of them here on this slide, and I'll talk on some of the subsequent slides about other things that we've added for being able to do tracking of different parts of the system to see what's going on. So the other big area that we've done a lot of work on is related to zones and OS virtualization is resource management. Because the two kind of go together. Resource management is almost always applied, certainly in our environment anyway, on a zone basis. So when you're talking about resource management, there's really 4 key areas that people want to manage and limit and control. There's disks, memory, CPU, and network. And so when we started building SmartOS, we actually had reasonable capabilities for memory and CPU, though I'll talk about some of the work that we had to do there. And network, we're in good shape with because we have crossbow and we can use VNICs and flows and actually kind of limit things that way. So we haven't really done much in network because we haven't needed to. But the big area that we were missing right from the beginning, and one of the first things that we had to solve was resource management for disk I/O. So we did this we did a couple of years ago, and we did this in the context of ZFS because that's the file system that we use. And I want to just go through kind of quickly how that works. So Bill and I did this project, and kind of our going in assumption there was that the I/O system can only really give you a few hundred IOs per second. And given that low number, it sort of rules out the possibility of doing things like capping your IOs or dedicating them to a particular zone. And then the other assumption really was related to latency. And so kind of taking that as our starting point, what we came up with was using the approach of doing a throttle on the I/O. And so I want to kind of go through, this has been in production now for probably close to 2 years. So I just, maybe some of you are familiar with this, but I want to go through just quickly how it works. So in order to do a throttle on I/O, the first thing we have to do is understand, what each zone's I/O usage is. And so, kind of running through, you can see the summary there. Basically, we're just tracking using a decayed average about how many IOs each zone is doing. And then we keep track of the overall latency for all of the I/O across the whole system. And by multiplying that together, we can kind of get a quick, very inexpensive measurement of what the usage is for each zone. So given that, then the question is well, when do we throttle a zone? And so, by subbing that together, we can, quickly see if one zone is using more than its fair share of the I/O. And one of the things that we did on that is we added a resource control so that we can, on each zone, we can sort of prioritize and say, this zone is a more important one, a customer is paying more money or bought a bigger zone, so we can actually bump up their priority through this resource control. So that calculation goes through to determine, okay, this zone is using more than its fair share based on that input that I just described, so it needs to be throttled back. So what we do is we actually throttle in 10 microsecond increments, and we ramp that up. If you continually exceed your fair share, we would ramp that up to a maximum of 100 microseconds per I/O. So what that allows us to do is, make sure that one zone isn't using more than it should when things are busy. The good thing about this is that we only throttle operations that actually go to the disk. So if you're doing your reads and hitting them out of the ARC, that runs at full speed. The other thing is that this doesn't even start until the disks we think are about 80% busy. So if you're doing a lot of I/O but your disk system can handle it, then things just run at full speed. So there's two tools that we built, two CLIs that allow us to actually observe kind of what's going on with your I/O. The first one is ZIO-Stat, and this basically allows us to watch the reads. Reads are more probably critical than your writes, because the writes kind of go into the transaction group and get aggregated together with all the other writes, so they're not usually as bad. But the reads that aren't coming out of the ARC, we want to be able to see on a per zone basis kind of what's going on with those. The other one, the other tool is VFS Stat, which is actually looking at the VFS layer to see what's happening with the I/O. And I've kind of highlighted in red over there the two columns that actually show you when the ZFS IO throttle is actually kicking in. So you can actually see here that this was on one of our build machines. You can actually see each zone there, how many delays per second we're hitting, and what the average delay time is that each zone is having when it's getting a delay. The next area that we had to work on, I mentioned, is we've got memory and we've got CPU, and those we had some capabilities in the system, but they needed some work. And in particular, memory capping wasn't that great coming out of the box. I mean, we had memory capping, but it had a lot of problems. It was implemented in the old RCAP-D daemon, which basically doesn't scale. It's inconsistent with all the rest of the system, and it can really get clobbered if a zone is misbehaving. So what we had to do is we redesigned the way memory capping works, so that instead of a single daemon trying to cap all of the zones, what we do is we have it now a thread inside zone atom D, and there's one zone atom D per zone, so each one is managing, kind of doing the management for that zone. So now the zone atom D will just manage the memory cap on the zone that it's managing. So it'll scale directly with as many zones as you're running on the system. The other thing that we did is we made it a lot more consistent, so that before you used to have to, the RCAP-D had its own tools and its own commands for setting the limits and looking at them and everything. Now it's all just done in the normal ways that you would manage the rest of the resources on the system. So it's really just a resource control that you set on the zone, and then that gets enforced by the thread in zone atom. And then monitoring all that is now just done through case stats, so it's much more consistent with the rest of the system. You can see here in this example, you can see the physical cap, what the value is set to. That would be what your resource control is, and then RSS is showing you what your current resonance set. So we've got like 67 meg the cap, and we're really only using like 24 meg there. And then we built a simple CLI that just consumes those case stats and shows you what's going on with your memory capping. The other thing I mentioned is that RCAP-D loses in a fight. That normally doesn't happen, but if you have a zone that's doing something pathological, or maybe somebody's trying to do a denial of service on the box, what can happen is if there's an application inside of a zone that's touching a lot of pages kind of just all the time, well, when we're trying to page those out, RCAP-D and that application can kind of fight with each other, and RCAP-D never really makes any progress because the app is continually just repaging in the pages again. So what we did is we actually implemented a page fault throttle that kicks in. So when we actually are over on your memory cap and we're trying to get you down, if we're actually not able to, we can actually start throttling your page faults, so that we start limiting how many page faults you can take in that zone. So if you have a pathological, normally this never happens, but let's say if it's deliberate or pathological, we'll throttle back your page fault rate so that we can be sure that we can keep you under your limit. And lastly, the way that this works, or used to work, is that when we try to page something out, we're really invalidating the mapping to the page. And so it used to invalidate the mapping across the board. And in particular, if you think back to what I said about sparse zones, that would be bad if you're sharing a page that happens to be like from user bin or something like that. every zone would be penalized because all of their mappings would be invalidated. So that was kind of unfriendly behavior. So we actually fixed the system so that when we're invalidating a mapping for a zone to get it under its cap, it's only going to invalidate for that zone. The last thing, this is a little bit maybe obscure, but there's a private system call that's used, or was used, still is used sometimes, in the system to figure out how much memory a zone is using. And that has to happen inside the kernel because we actually have to look across pages and kind of figure out shared mappings and things to determine really what the total usage is for the zone. And we had problems with that where we actually were seeing latency bubbles coming in on the system because when we're trying to sum up and figure out how much memory is being used by a process, that actually stops the process for a little bit. So we were actually seeing some latency delays happening when the daemon would run to actually look and see how much, to see if you're over your cap and things. So we actually dramatically reduced the amount of time that the system actually uses this private system call so that we use a faster, cheaper calculation most of the time so that we can avoid most of those latency bubbles. The other area that needed a lot of work was, or some work, was in the area of CPU scheduling. And so I want to just take a quick digression here and talk about that for a second. There's two things in the system related to how we schedule CPU in a multi-tenant environment. First off, we don't want to do things like pools because that's sort of a partitioning of your resources, and that sort of goes against the whole idea of what you want to do in a multi-tenant situation because you're not getting the best resource usage. You typically be wasting a lot of things. So we never use partitioning. We always just share all of the CPUs across all the zones. And then we take advantage of the two capabilities of the system, CPU caps and the fair share scheduler. And there's some work that we've done in both of these areas. And in case you're not familiar with CPU caps, the idea here is that sets an upper limit on your CPU utilization when there's idle CPU, so that you could go more, but you hit your cap. And so we won't let you go more. And the idea of that really is to give you consistency. If you're the first tenant on the box, you don't want to think everything's great, and then next week all of a sudden more tenants are on the box and you're getting a lot less CPU. So we can sort of set an expectation right up front. The other thing is the fair share scheduler, and that really lets you sort of deal with the situation when you're overcommitted, you have more work to do than you have CPU resources, and that's the fair share scheduler basically kicks in at that point to determine who should run next to make sure nobody's hogging the system. So in the area of CPU caps, one of the problems that Brendan actually found, this is his picture right here, is that it didn't work as well as it should, and we had to fix this. Basically, you can see from this graph that as we got a lot of threads running, we weren't able to really go up to our full cap. And what Brendan did was sort of show that when we turned the clock up from 100 hertz to 1,000, we could actually run a lot better. And once we debugged this down, we realized that what was happening is that CPU caps, when you were at your cap, was only dequeuing one thread each tick. And so we weren't able to get enough work to really keep up to our cap. So the fix that we had to put into the scheduler here was that we sort of look and see how much usage you have and how many threads you have in the queue. There's a special queue when you hit your cap. And so we actually dequeue more than one thread at a time and kind of scale that up depending on how much work there is to do so that we can actually keep that zone running at its cap instead of at a much lower rate. The other thing that we did with CPU caps is what we call bursting. And the idea with bursting is really, we want to let you use more CPU than you've actually bought, as long as CPU is available. And the idea here really is that, if you think about lots of tenants being on the box and carving, mentally carving up the CPU on the box, potentially that's a fairly small amount of CPU that's available to each tenant. But if there's excess CPU that's available, why not let people use that? So the way this works is we have a RCuddle that you can set on the system that essentially defines what your baseline CPU is. This is kind of how much of the box you actually bought as a customer, assuming the box was completely provisioned out. And then, then when you're over that baseline CPU, then you're actually sort of in a bursting mode. And then when you hit your cap, then you actually just can't use any more CPU, until you kind of degrade below your cap again. So the idea with this is that, you can sort of on demand and instantly get more CPU than really you paid for as long as the CPU is available. And we also added another RCuddle called the burst time, which allows you to, we don't actually, within SmartOS, we don't actually ever set this, so you can burst indefinitely, but as part of this implementation, you can actually set a number of seconds that a customer could burst before they would actually cap down to their baseline. And so you can actually track this now with more case stats that we added, so you can see, I think you can see it. So in this, the value right there, 400 means 400, you're essentially getting 4 CPUs, or 400% of one CPU is what your cap is set to, and then your baseline, you can see there is, should be set to like 80, so you've actually bought 80% of one CPU, but you can actually run all the way up to 4 CPUs, before you would get capped down. So that's CPU caps, which is what happens on the system when there's excess CPU. Fair share is what happens when you have more work than things are backlogged. And so just to quickly contrast this with time sharing, which was probably what most people are familiar with, and which is the default scheduler in the system. Basically time sharing is supposed to give you a round robin effect. So each thread that is ready to run gets its shot to run. Of course, the problem with time sharing in a multi-tenant environment is that if one zone has a lot of threads and another zone only has a few, the zone with a lot of threads is going to get a lot more CPU, so that's not fair. So fair share basically works on the collection of threads instead of on a per thread basis. And this has been in the system for a long time, so it's, there's an RCuddle to set the share that each zone gets. Now, I get people are always confused about fair share scheduler because they think of it as somehow partitioning up the CPU or a percent of CPU, and that's not really what it is. Fair share, basically, that share RCuddle value is just a number that's used as an input as part of the scheduling calculation to determine the thread's priority to determine what thread should run next. So it's important really to not get confused about that. Now, actually, Brendan's talk sort of showed a nice example about how virtual CPUs with VMs schedule onto real CPUs. So VMs in some ways are kind of simple because a typical VM may have 2 or 4 virtual CPUs, something like that. So there's only a handful of threads that the operating system actually has to deal with. There's like 1 thread for each virtual CPU and then a few threads for like some I/O and things. But a VM doesn't have very many threads actually running inside of it. One of the nice things about OS virtualization is you're getting all of the threads. If your app has 100 threads that can run, we can actually see those threads and we can schedule them and we can dispatch them, and potentially we can get a lot more work running through the system that way. So this is actually the same example from Brendan's talk, that one of the problems that we had, just to go into a little more detail on this one, was that within a zone, the fair share scheduler wasn't giving us the right timeshare behavior. So if you had, the way Brendan set this configuration up, you can see that you had 4 CPU-bound threads, but we're actually seeing that sometimes these threads don't run for many, many seconds. So you want to see inside of the zone, you want to see the nice time-sharing behavior, which is independent of across all the zones, that you want to see the fair sharing giving each zone its right thing. So we had to actually fix the fair share scheduler to deal with this case. which we did. We fixed it as a special case. But the implication of that really is that the calculation that the fair share scheduler is doing to determine the priority of each thread really isn't quite right. And so, you know, we sort of have seen this in other cases where, you know, sometimes from our operations side, you know, people are telling us, you know, it seems like I don't always get, you know, a zone isn't always getting as much CPU as I think it should get. You know, and kind of, I've tried to sort of recreate that situation where if you have a zone which has a few runnable threads and compare it to another zone that has more, in this simple example here, I just have 2 zones with the same amount of shares and 1 thread and 3 threads. You know, I would expect to see pretty close to 50% coming out on each zone, but in fact, the zone that has only 1 runnable thread is always getting a lower percentage of CPU. Now, I've been working on the fair share scheduler looking at this recently, and I don't have a good solution to this yet, but I did track down part of the problem is actually not in the fair share scheduler, but is actually in the way that microstate accounting was actually keeping track of how much CPU each zone was using. So there was kind of a little bit of a bug in the code that if it had to loop around and do some things, it would kind of calculate things incorrectly. So excuse me, that's been fixed, and we actually get a little bit better percentage now on that than what we were getting before. But we're still seeing this a little bit low, and you know, part of it is just, you know, the more work that each zone has that can be scheduled, the better it's going to do. But we want to try to get this as close to 50% as we can. So one of the things that we put into the system is some additional stats that we're tracking on a per zone basis, and I've added an SDT probe in the fair share scheduler, and you know, we built this simple FSS stat as a simple dtrace script that we put into the system that lets us actually track kind of all the different inputs that are being used by the fair share scheduling algorithm, so that we can try to get a better handle on what's going on and why particular zones are being scheduled, when they're being scheduled, and what their priorities kind of coming out to be. So I think that this is an area that still needs more work. You know, we built some of this stuff here that I've described to kind of help us understand that better, and we've made a few fixes here, but this is still something that I think is an area that has a little bit of room for improvement, although I've tried actually tweaking the algorithm a little bit, and I haven't actually been able to make it come out better than it is now, so I still need to do some more work on that. So just wrapping up, you know, kind of summarizing all the different things we've done for OS virtualization. You know, we've got our brand, fixed a lot of bugs, a lot of enhancements that we put into the system, things, you know, in SMF and services and whatnot, dtrace, all the case stats. We've done a lot of work in the resource management area that we've just gone over. So I think overall, we're in a lot better shape with being able to run this with OS virtualization in a cloud type environment than we were a couple of years ago. So that's a really quick overview. Any questions before we go to the next presentation?
Two questions. What happened to LX zones, and can you suspend, resume, checkpoint, migrate zones of either type, and perhaps a whole bare metal OS?
Okay, so there were 2 questions there. The first question was, what happened to LX zones? So those were removed from the system back in the Sundays before Open Solaris was closed off. And the problem with LX zones, the reason they were removed is they really only emulated a 2.4 Linux kernel, so it was pretty dated and kind of not very interesting. It hadn't been kept up, you know, to emulate the latest kernel that people have been running now for many years. So considering that it was really pretty obsolete, and there wasn't, the data at Sun that we had back then showed that there wasn't hardly anybody using them, so the decision was made to take them out just as a maintenance issue. Code's probably still out there if some, from the old Open Solaris tree if someone wanted to resurrect it. But
there's a patch that's passed around.
Okay, cool. I mean, so it's, yeah, I mean, if somebody's really interested in that, honestly, if you want to run Linux, at this point, you're probably better off doing it in KVM than in Alex Zone, but if someone's done that, that's cool. Let's see, the second question was about being able to checkpoint a zone, stop it, move it, migrate it. Because, and to answer the question, basically, no, you can't do that in general on all of that. Because you're dealing with a single operating system kernel, there's a lot of state in the zone that's sort of smeared across both user land and in the kernel and not really easily extricated out of the kernel to be able to sort of put that to the side and put it back into the kernel later. So we don't have like hot migration or warm migration of a zone, and we don't have a way to suspend and resume a zone. Conversely though, because a zone is such a lightweight thing, it boots up in 2 seconds or 3 seconds, depending on your hardware really, and how much stuff you're starting up. So it's, super easy, to basically just shut a zone down, move it, or even already have it sort of pre-deployed to another box and boot it back up. It is a disruption and you lose your in-memory state, but that's one of the trade-offs really of that kind of virtualization versus like a VM, which is more of an encapsulated thing that's a lot easier to take and move to another box. Any other questions? Oh, one more here.
Yeah, can a customer inside a zone observe how much burst time they're using? Or is that only available in the global zone for someone to look at?
The question is can a customer in a zone observe how much burst time they're using? And the answer is that yes, they can. I mean, that's a per zone K-stat. So inside of a zone, you're allowed to look at your own K-stats. And so you can actually see what your baseline CPU is. You can actually see how much you've been over your baseline. And in that K-stat, what I showed on that earlier slide, all that data is available inside the zone.
You mentioned the throttling the ZFS IO. Is that only to reads, and have you done anything with writes?
The question is on throttling the I/O. Does that apply only to reads, or does that apply to writes? And I'd have to double check the code, or maybe you could correct me, Bill, but I'm pretty sure it applies to both because we're doing that at the VFS layer. Once we have to throttle, we actually are doing that at a higher up layer. So we actually, can do both. We could throttle both your writes and your reads.
We almost never see it in reads. Is it cache?
Well, it depends. I mean, if you're hitting the cache, then yeah, those just go at full speed. But some workloads, are missing the cache for various reasons, and those are the ones that are actually problematic because that's, what you care about is, taking the, your total I/O budget off your disk subsystem. And so, if you are hitting the disk a lot, that's when we start having to worry about it. But since we are doing the throttle up at the VFS layer, we actually can do it for both reads and writes. Oh boy. How about you?
If somebody's provisioned an entire machine and have decided to just whale on the disks, how do we make sure that the throttling stays out of the way?
The question is, if someone's provisioned the entire machine, how do we make sure that the throttle, the ZFS IO throttle stays out of the way? There is a setting we can actually just disable the throttle altogether if you don't want throttling at all.
Right.
But the thing is, if you provision the entire box and you're really the only zone on the box, then you're not competing with anybody, so you're going to get all the I/O anyway. But you could turn off the throttle if you don't want it. It's really, it really only matters when you've got multiple zones and multiple tenants. You want to make sure one tenant isn't messing up another one. But yeah, you can turn it off if you want. All right, last question, and then I think we're out of time here.
Thank you. Did you port GPL KVM code or just the ideas? And can you run Windows Server under your KVM?
The question is, did we port the GPL KVM code or just the ideas? And we did port KVM. I mean, it's the same code base. It's in its own repo. it's funny, the licensing thing. Actually, you can actually hear more about the licensing thing if you want to go watch Brian's talk from the KVM from last year, because that was a question that was raised there as well. But it is just it's just the standard KVM code. And what was the other part?
Windows Server?
Windows Server. Probably, I don't know of all. I mean, we've run a lot of different OSs inside. I mean, a lot of different Windows and Linuxes and things. I don't know if we've run Windows Server specifically, but I would. It should. If it doesn't work, that would be a bug we want to fix. Okay, somebody said 2008 R2 worked fine. So.
2008 and 2008 R2.
Okay. Good.
There is a question on the stream. Are Joyent doing any work to get NFS servers working in zones?
The question is Joyent doing any work to get NFS servers working in zones? So that we're not doing any work on that right now. Unfortunately, that was one of the projects that was happening at Oracle. That when they shut down Open Solaris, that project hadn't integrated yet. So so we don't have the benefit of the work that they did there. I mean, I know that it's doable because it was done by Oracle to enable that, and actually it's probably not that much work to make that. It's probably a lot of just going through and cleaning up little bits and pieces here and there. But we're not currently doing that work. Okay, great, thanks a lot.